Today we're going to do number 543, diameter of binary tree. So we're giving a root of a binary tree and we want to return the diameter. And the diameter is the length between the two nodes of the longest path. So here the longest path is 4, 2, 1, 3. So 1, 2, 3. That's the length. Or is 5, 2, 1, 3, also 3, and that's what we return. So when we think of these longest paths, it's the longest depths. So we can do DFS search. And we can use recursion to do it. So here we can see what's the diameter of this node. And then we do what's the diameter of this node and so forth as we do a DFS. So the first one will be a brute force where we calculate every possible diameter from this node. So here 1, 3, and then 1, 2, 5, and then it'll go all the way down. Get the height of, so we do that, get each node. And we do that by getting the max height of left subtree, max height of right subtree, and then we find diameter, which is adding left and right. And lastly, we can, whichever has the highest diameter is what we return. So we'll return back the maximum diameter for every possible route. So here the time complexity will be O of n squared because we're calculating the diameter. So for this one, we have to look at every possible combination. And the space complexity is going to be O of h, where h is the height of the binary tree to hold the call stack. So how else can we do this? Another clever way is to do a bottom-up approach. And here we send up the height of each node and then use DFS. We use global diameter variable, and then we calculate the updated diameter as we go up the recursion. In this way, we just have to go all the way down and then it sends it up. So it's only going to be O of n complexity. And the space complexity will stay the same of OH. So since this has a better time complexity, I recommend we do a bottom-up approach with DFS recursion, but I'll show you both ways. So for the bottom-up, we create the variable that diameter starts off as 0, and that's what we're going to return. And here we're going to do a function DFS, and we're going to call it with the root. So when we do DFS, if it's null, return 0. And here we're going to get the left side, const left height equals DFS node.left, const right height equals DFS node dot right. And we can update the max. So diameter equals math dot max. Is it the previous diameter or left height plus right height? And now we want to return one plus the max of either left height or right height. Great. So let's do it the other way as well. So here we have to calculate the height. We can create a separate helper function. And here, if there's no node, return 0. And then we can calculate the height. So 1 plus math.max, either the left side height left of the node or height the right side of the node. And now we want to do DFS through it. And we're going to return this DFS because it's going to have the diameter pass it through it. I like to do this so I don't forget that we have to return it. And now the same idea, if it's null, the node, return 0. And now we calculate the height. So const left height equals height node dot left const right height is height node dot right. So here's the change, because for each one of these nodes we have to keep calculating the height each time, but we have the diameter. So const current equals current, let me see, diameter equals left height plus right height. And now we just return the max of the diameters. Return math.max current diameter, or as we keep going through the DFS, the left side, or DFS of the right side.